Welcome to another video in this big O notation series. In the previous video, we talked about the time complexity and we gave an example of the different type of time complexity. And in this video, we are going to explore space complexity. We already talked about what is space complexity at the beginning of the previous session of this video. And we also talked about the memory allocation of each variable type. So now we want to consider the big O notation for space complexity because it also contributes to how good your algorithm is. The first one we're going to look at is the constant space complexity. So what are the criteria? The first criteria you will see is the algorithm does not depend on the input size. So when an algorithm does not depend on the input size, the algorithm is said to have a constant space. And the next criteria you want to notice is the constant memory usage. So the variables that are used for this algorithm, they are constant. They remain the same throughout the algorithm processes. So the next criteria you want to see is no dynamic memory allocation or deallocation. This means that the algorithm does not allocate memory dynamically based on the input size, and also any required space or memory of the algorithm is predetermined and does not change as the input size. The next one here is in-place operation. So this means that the algorithm performs operation directly on the input data without requiring additional memory. This is like changing the value in place. For example, an array using an index to replace the value of an array. So that is an example of in-place operation. Okay, the next one you will see is fixed size data structure. So the overall of this is the space required by the algorithm does not grow with the input size or the size of the data structure on which we are using the algorithm. So let us look at a code example. So guys, if you look at this function, you will see that this function has an input of 19 and 2, right? And you can see there is no any other allocation of memory. So we are just checking if one is greater than the other and we are returning the biggest of the number. So the space complexity of this function is O of 1, which is constant time. You can also pause the video and assume, or you can determine the time complexity of this function. However, the time complexity of this function is also O of 1. O of 1 time and O of 1 space. All right, so let us look at another example here. And if we look at this function, so what this function is in is to reverse an array. So this function has an input of an array which has been passed in here as an argument and is here as a parameter. So what this function is doing is taking the start and the length, and we're using that start and length to reverse the entire array. This operation here is an example of what we call in-place operation. You can see we are changing the value of an array at a particular index using the index number. So there is no allocation of memory. All we are doing is just to change the value in place. So this function can be regarded as O of one space, which is the constant space. And you can also pause the video and determine the time complexity of this. So the time complexity of this is O of n time. Okay. So next, let's see. Okay, we have one more example, and this example is find marks in array. So what we are doing here is we are searching for the biggest number, like the largest number in an array. So you can see this function takes in array as an argument, and we are setting the max value starting from the first index. So at this position, we are searching for the max value. So I want you to take note of something, that no dynamic memory has been allocated here. It's all fixed. It all was fixed. You can see this one is fixed. And what we are doing is change that value if one is greater than the other. So this is O of one space, and you can also determine the time. So the time of this, time complexity of this is what? O of n. All right, so that is all. And the next one we want to look at is the O of n, which is the linear space. So guys, when we talk about the O of n linear space, the first criteria you want to see is the memory usage is directly proportional to the input size. I expanded on this in one of my video. I will urge you to check the module, and you're going to see where I visited the chart. I even created an example for this. So whereby the memory usage is directly proportional to the input size, this is regarded as O of n. Another criteria you want to see is linear memory usage. So this is kind of the same thing as directly proportional to the input size. So when we talk about the linear memory usage, you can visit the big O sheet, for example, and you're gonna see something like this. You're gonna see something like this where um let me see, this is, if this is the input, and this is the size, this is the size, so it's directly proportional to the input size. So you can see this graph shows that the more input size, the more memory will be used. So another criteria you will see here is the algorithm stores the entire input data. Okay, another one is algorithm that construct data structure that grows with the input. So all these four criteria I'm giving here all relies, or actually referring to this example I'm giving here. Okay, so let us visit VS Code to explore some code example. So I am currently on my VS Code, and I have a function here which generates an array. So all I need to do is to pass in a number, and after passing in a number, it's going to generate that length of array for me. So, and you can see in this function, we created an array. Definitely this one here you're seeing is an empty array. Okay, but where the process of O of n space is coming from is, while we are creating the array, we are adding the item into the array. So this line here makes this code O of n operation. So after the O item has been added to the array, we want to return the array. Okay, so I think I should run this. Let me run this so that we can see. Okay, you can see it generates 5 array. If I change this to 10 and I save, run this, you can see it generates 10 value. It generates 10 value in the array. So this function is O of n. And as a bonus, you can also pause the video and determine the time complexity of this algorithm. So the time complexity of this algorithm is O of n. Is O of n time. Okay. The reason for O of n is this. We are looping through a particular value. I expanded on this in my previous video. I'm going to drop a link in the description to ensure you visit the video, and that is in case you don't understand how to identify the big O notation of time complexity in code. So alright guys, the next one we want to look at is the logarithmic space complexity. Okay, so guys, for this algorithm, to determine the space complexity, the first thing you will see is it's a sublinear memory growth. What does it mean? This means that as the input size grows, the memory usage grows much slower compared to the linear growth. Okay, so it is not directly proportional to the input size. It is like half of the growth. I'm going to give a more clear example. So another criteria you will see is the divide and conquer approach. So this algorithm does follow the divide and conquer approach, where the problem is recursively divided into smaller sub problems. So when we say sublinear, let me just give a small example here. So if we say that the input size is 10, for example, so for the memory allocation, right? So it's going to be half of this, and the half of this is going to be what? 5. Half of this is going to be 5. Okay, so um, this is what we call linear memory growth. And there is also divide and conquer. So what divide and conquer is, maybe for example, I have a big problem like this. And to solve this problem, I have to divide it into 2. And when I divide it into 2, so I work on this part first. Then when I'm done with this part, I will go to the other part and solve this problem. So any algorithm that uses this kind of architecture, it is regarded as what? Divide and conquer algorithm. So let us visit VS Code and see some example. So guys, I have a very popular algorithm here which is called binary search. Okay, so if you look at a binary search, what it does is it accepts an array as an argument and a target. So we want to search for a particular target in this algorithm set a high and low bound, and I touched this in more example and visualization in my previous video. So you can see what we are doing here. At each process of this algorithm, we are breaking the array into smaller array so that we can actually look for the target more easily. So you can see the first thing we'll do is to find the middle of the array, and when the middle has been gotten, so what we do is first of all, we are checking this part. If the array is equals to middle, we just return that it has been found in a particular index. Or X, we are breaking that array into smaller units. Okay. So this particular process is what make this algorithm O of log n space, because it break down the array into smaller size. You can see where the array is being, the value of the array at a particular index is being compared to the target. So this array is being manipulated using the low and high. All right, so I think I don't need to run this because this is a very popular one. So I think this is clear enough, right? So the next one we want to go to is the big O of n raised to power 2, which is the quadratic space complexity. So guys, the first criteria you will see is a nested data structure where element grows quadratically with their input size. So what is happening here is the input size or the data itself will grow quadratically. So let's say, for example, right, there's an input of 10, right? So the algorithm is going to generate a memory which is greater than the input size. So it can even be times 2, it can be 20, or it can even be 15, right? So I'm just using this figure as example, whereby the algorithm generates a memory which is greater than the input size. So this is regarded as what? N raised to power 2. So the next one you will see is double nested loop with memory. You can see with memory. That was why they put it there. So it must be with memory. So it means that the space is depending on a nested loop. So let us go to VS Code. Okay guys, so I have a code example here. I have a function which is called generate matrix, and I'm going to show you why this code is the big O of n raised to power 2 space. So it all happened here. Let me just, yes, here. Okay, so this is the first loop, right? This is the first loop, and this is what the nested loop. You can see we allocated a space here. So when this space is allocated here and we loop, note here, we generate another variable here. So this space is O of n. This space is what? O of n. Now, for every loop, we are going to create this space. So that is why this one is O of n. So if you look at the nested loop, we have another operation going on here. So you can see an item is being added to this row. Okay, so this operation is O(n) squared because we are creating a space here for every loop, and we are adding an item to this variable called row in the nested loop. And overall, there is another addition is going here. So we're adding this row to the main matrix. So this operation here is what big O of n space. I think it is important I put space here. So this is space and this is space. We can now say that this algorithm is what? O of n raised to power what? 2. Okay. So as a bonus, you can determine the time complexity of this code. So I'm going to tell you that this time complexity of this code is O(n) squared. So this is what? O(n) squared, O(n) raised to power 2 of time complexity. All right, so we have another example at the bottom here. This is what generates all pairs. So what this function is doing is going to generate all pairs. All right, so if we look at it, we have a nested loop, and we already talked about that here in this slide. It says double nested loop with memory. Okay, so we have a variable called pair, and what you are seeing here is this variable is depending, right? Is appending item to the array. Sorry, I made a mistake here. Sorry, this is also on square. This is what on square. This on square. So we just have to pick one out of there. Okay, so this pair here, what you are seeing here is we are looping on every item and we are adding an item into this pair. So this memory is not only depending on this one, on the first loop, right? It's also depending on the nested loop. So in that case, we can say this algorithm is the big O of n raised to power 2 space. Okay, right? So because of this part of the code. And for bonus, this is also the big O of n raised to power 2 time, right? So the time complexity is n raised to power 2, and the space complexity is also n raised to power 2. So all right guys, we next we want to look at the big O of n log n, which is the linear arithmetic space complexity. So guys, just like time complexity, when you see the big O of n log n, which is the linear arithmetic space, just know this is the combination of O log n and the combination of O of n. So these are two operations combined together as one. So the first thing you will see is an algorithm that does the divide and conquer with logarithmic depth. Okay, so it's doing the big O of n space and also the big O of log n space all together as one. So we have an example here, which is merge sort. Okay, so let us look at that in the VS Code, right? Okay, I'll be using quick sort rather. So, okay, let me use quick sort. Okay, so if we look at quick sort, this quick sort algorithm, so we have an array here and we are passing it to the function here. So I want you to take note. This is where we're dividing the array into two. These are pivot. This pivot is going to use to divide the array into two. So the array will be divided into left part and right part, and this is also what the middle. So there is now a recursive call that does the operation. You can see this is the this is a recursive call. So this operation is the combination of big O of n space and big O of log n space. So altogether, it's going to give us the n log n. Okay, O n log n and log n space. Okay, so this is a clear example of an algorithm that is doing the divide and conquer with logarithmic in depth. So as a bonus, you can also determine the time complexity of this. So this is obvious. The time complexity of this is the same. So this is also the big O of n log n time. Okay guys, so next we want to look at the big O of n raised to power 3, which is the cubic space complexity. So guys, this one is pretty straightforward. So you can just remember the big O of n raised to power 2, which is the time. So you just like adding extra one loop to it. So that is why it's called a triple nested loop with memory usage. So the memory usage is depending on the triple nested loop. So the second criteria you see is a nested data structure with cubic growth. Okay, guys, let us look at example in the code. Okay, so we have a function here which is the cubic space. So the cubic space, it takes in a matrix value. So where I want to attract your interest is the triple nested loop. Okay, you can see we have a nested loop here. We have a nested loop here. We have another one here, and we have another one here. So you can see this is the result. So the result is now depending on the three nested loop. Okay, so this is what make the algorithm the big O. This line here is what make this algorithm the O of n raised to power 3. Okay, because it depending on the 3. So note that if this had been here, because this is under the second nested loop, so this would have been n raised to power 2. Okay, and if this would have been here, this would have been n raised to power. This whole algorithm would have been okay. Some are still depending here. Okay, some are still depending. So if I remove this part, and this code is here, so this would have been n o of n. This would have been o of n space. So, but because the algorithm need to work in this fashion, so this part of the code is what make this code O of n raised to power 3, which is the cubic space. So you can also imagine the time complexity of this. I think you should know now. So the time complexity of this code is n raised to power 3. Okay, for the time complexity. So same thing for space and same thing for time. All right, guys. So next we want to look at the big O of 2 raised to power n. So guys, the criteria for an algorithm that has the big O of 2 raised to power n exponential space, the first criteria you will see is exponential data structure. So this involves the data structure with an exponential number of elements, because the algorithm needs to perform an operation for each possible combination of the input elements. So this also means that the time taken by the algorithm doubles with additional input elements. So the next criteria you will see is the algorithm must use the 2 raised to power n units of memory, where n is the size of the input. So we can see examples like generate all subset or combination. So this algorithm is regarded as the big O of 2 raised to power n space. We also have another example, which is exponential recursive call. This is also the big O of 2 raised to power n. So let us go to VS Code. So I have a function here which is called power sets. So this power set takes in an array of number and is going to generate all possible sets. Okay, so if we look at what is going on here, you see there is a space here which we have defined. We have defined a space here. So the time complexity for this algorithm is big O of 2 raised to power n. And also the space complexity, let me put it time, and the space complexity is the same thing, which is 2 raised to power n. 2 raised to power n space. All right, guys. So next we want to look at the last one. So this is called the big O of n factorial, which is the factorial space complexity. Okay, guys. So an algorithm that has a space complexity of n factorial is when an algorithm is trying to compute all possible permutations of the input. So as the input size grows, the amount of memory used by the function also grows exponentially because you have to store those combination in a particular variables. So I have a code example here, which you can see. So I have a function which is permutate, and what this function does. Okay, let me run it so that we'll see the result on the console. I think I should clear my console first. I'm gonna move this up a little and run the code. Okay, you can see this function generates a permutation of these numbers. So you can see there is a variable, right, that holds all the different permutations. So whenever all these combinations are being generated, so we're going to store this number somewhere. We're going to store this value somewhere. So I want you to note something, right? You can see there is a loop here and there is a nested loop. So in the first loop, we are holding the remainder, and in the second loop, we are doing a recursive value of the remainder. Then after the recursive value, that is when we want to store the permutation. Okay, so let me debug this. So let me just debug this so that we can see. So I have put in the breakpoint here. So I'm going to run in debug mode, and so that we'll see what is going on for this. So I'm going to use F11. You can see it here to move to the next step. So I'm going to step in. So you can see this is where we create a variable, and you can see the variable has been created here. You can see the variable has been created here. You can see. So next, I also want you to keep your eye on the call stack. If you look at the call stack, you can see this is the initial call, which is calling of the module, and this one on top here is the current process that is going on. So if I do F11, and okay, I think I should expand this a little. Okay, good. So if let me expand this. Okay, this is not going. Okay, all right. So if I do F11 again, you can see this is the remainder, and yes, if you look, we now have what the remainder, which is 2 and 3. So now there's going to be another recursive call. There's going to be another recursive call for the remainder, which is for 2 and 3. So I'm going to press F11 to step forward. You can see the algorithm did not get here, but rather it was suspended in the call stack. This is it here. You can see this is it here. So this is the current one this is the current process that we have, and this is the one that has been suspended. So until this one is completed, that's when we're going to move to this. So if this one, if this call have another recursive call, this will also be suspended. So it will continue to suspend until there is no recursive call. So now there should be another remainder. You can see the remainder is now 3. So if that goes, you can see the first one, the second one has also been suspended. Now we have another call on the call stack. So this is going, and you can see this has also been suspended until it is empty. So now you can see since it's empty, it moved to this line, which is line 8. So that's when all the suspended call stack will begin to get call, or they will resume again. So it's going to continue until all value has been added to this permutation. So you can see if there is a sub remainder, there is also going to be another recursive call, and that's what you've seen. That's what you are seeing here that is happening. You can see there's also another recursive call for each item until it is empty. So it continues in that fashion until it generates the results. So the takeaway here is this algorithm is the big O of n factorial, and let me put it, which is for space, and same thing for the time, n factorial for the time. We should always try to maintain the big O of 1 or O of n or O of log n, or at worst case O of n raised to power 2. Or you can still manage the big O of n log n. Anything above that is not a good practice. You can find a way to refactor your algorithm so that the performance will be good. So all right guys, if this is your first time of coming to my YouTube channel, ensure you hit the subscribe button, because I'm going to cover a whole lot. We have a whole lot to cover in this series. We are going to cover the implementation and a whole lot. See, so ensure you like, ensure you subscribe. So guys, thank you very much for watching. I will see you in another video.